So my name is Kevin Lannon, and I'm a professor in the physics department here at Notre Dame. And I also am the coordinator or co-coordinator for scientific computing within the U.S. university facilities for the compact muon solenoid experiment, which collects data from proton collisions at the Large Hadron Collider, which is at the CERN lab in Geneva, Switzerland. The science that we're trying to do at the Large Hadron Collider involves looking for things that happen only very rarely in collisions between protons. So for example, we discovered the Higgs boson at the Large Hadron Collider, and to do that, we had to make many proton collisions because you only get a Higgs boson maybe once every 3 billion or so collisions. So to be able to sift through all the data that you need to sift through in order to make a discovery like that, you have to have some form of scientific computing. So I would say it's not even that scientific computing is valuable, but it's essential. We can't do our research without it. The type of scientific computing that we use for the Large Hadron Collider is something that's known as high throughput computing. So the basic idea is that any individual proton collision that we want to analyze can be done separately from all of the other collisions and doesn't really take that much time or computational resources, but we have so many of them to analyze that we need to harness a large amount of computing in kind of a very parallel way. And so we use computing from all over the world together to try to solve this problem, and that's really where things like distributed computing and those sort of techniques come in. I'm very interested in using tools that help me harness large-scale resources that are spread out among a number of different places. So for example, we make heavy use of batch systems like the HT Condor batch system. We also have a lot of data that we need to move around, and so tools that help us move data are important, things like XRootD, which is a tool that lets you stream data almost the same way that you stream movies over Netflix. And I promise that Doug Thane didn't pay me to say this, but I am very interested in tools that make my computing tasks portable and able to be distributed widely. And Doug's lab really builds tools like that. Things like Parrot and WorkQ are things that let us take our work and do it in a number of different places. As co-coordinator of U.S. university computing facilities, one of my primary priorities is to find a way to tap into the computing resources that are present on most university campuses but maybe aren't being leveraged for our LHC research. And here at Notre Dame, actually, that challenge has come to the forefront thanks in large part to the Center for Research Computing, which provides, or I should say hosts, a very large scale of computing resources, over 25,000 CPU cores. Now, most of those resources belong to faculty members who have purchased the systems for dedicated purposes with their research groups. But the CRC has a policy that any computational resource that they host that is not being currently used can be used by another member of the community on an opportunistic basis. So at any given moment on campus, there may be 5,000 or 10,000 CPU cores which aren't being used out of the 25,000, just naturally because that's kind of the ebb and flow of scientific research. And if we could find a way to tap into those resources, that would provide a set of computing resources that's at least as large as any of our dedicated computing facilities at universities. And so working together in a team with physicists and computer scientists and harnessing tools in particular from Doug Thane's group, we've managed to tap into those resources, and it's been a really successful way to make progress in our research. So I would say the biggest challenge is that as we push forward at the Large Hadron Collider and similar experiments, we're increasingly looking for things that are more rare, which means that we need to collect more data to try to find them and to sift these the data out from an ever-increasing pile. At the same time, because of the realities of the way we increase the data volume, the data is also becoming more complex. So projections suggest that we're going to need at least 5 to 10 times as much computational resources to keep doing the physics that we're doing, but the budgets are not going to support that kind of growth in resources. So we have to find new ways, new paradigms of analyzing the data that will let us do more with the resources we have and really overcome this challenge so we can break through to the next discovery. I think the best advice that I could give to somebody new to scientific computing is to realize that scientific computing is about determining what's possible in science. And so don't take anybody's word when they tell you that something is not possible. A really great example is a student that I've been working with for a while now, and her research goal for her thesis was to do an analysis that required a tremendous amount of computing. And I think anybody that she talked to would say, listen, a graduate student is just not going to be able to access that level of computing. But she looked at the problem, and she collaborated with other scientists and computer scientists and wrote software that we call Lobster, for reasons we don't need to get into, that let her access the resources here on campus that no other graduate student would have been able to access without the software that she and her colleagues created. And that allowed her to do her analysis that would have been impossible under any other circumstances. And it's because she understood scientific computing, and she collaborated with people both within her field and also other fields, in particular computer science. And that's really what we need if we're going to make another breakthrough.